With that, I want to introduce our first speaker, John Mankins. I've known John for I don't know how many years, decades. But John is president of Artemis Innovation Management Solutions, LLC, and of Mankins Space Technology, Inc. He's also vice president of the Moon Village Association and serves on the boards of both the National Space Society and of Space Canada. And most recently, he's joined the faculty of the online Kepler Space Institute. During his 25-year career at NASA and JPL, he held numerous positions, including serving as chief technologist for human exploration and development of space at NASA headquarters, where he received the National Exceptional Technology Achievement Medal and managed the $1 billion per year Exploration Systems Research and Technology Program. John's best known for writing in the early 1990s the first detailed definitions of TRLs, technology readiness levels, and as the world's leading expert in the field of space solar power. He lives with his family on a ranch on the California Central Coast. John.
Thank you, Rand, for that kind introduction. It's a real pleasure to be with such a distinguished group of thinkers and visionaries on in a discussion of what I think is going to be a very important topic. This morning, my topic is going to focus on lunar south polar mining as a subset of the larger topic of space mining and space resources. And I thought I would begin with past visions, going back to Jules Verne in 1865 and the From Earth to Moon, which was extraordinarily prescient, sending a first human mission from Earth to Moon with a launch from Florida. And then after some lunar adventures, a return to Earth to splash down in the ocean and be picked up by a US warship. Almost exactly the same end-to-end mission concept as was actually implemented 104 years later. A key factor in the Jules Verne vision was that it was a private venture. Later thoughts about the moon included the idea in the 1895 of lunar gold mining, and in the extremely beautiful and visionary German silent film Frau und Mond in 1929. Once again, the motivation for a private venture going to the moon was space resources, the idea that there might be gold on the moon. And so from the earliest days of at least fiction, there has been considerable interest in the moon and its resources. In 1963, in explaining the venture to go to the moon within this decade by the United States government to the US Congress and the American people, a beautiful small booklet was put together. If you have not seen it, I highly recommend it to you, called Why Land on the Moon. This was in 1963 by Dr. Robert Jastrow and Dr. Homer Newell. And it has these beautiful etchings of what the lunar mission might look like, and explained the purposes of going to the moon as relating to understanding the origins of the Earth-Moon system, understanding the origins of our solar system, and to essentially develop new technologies and capabilities, and to establish on the geopolitical stage that the US was in fact a country with whom to partner and whose system of government and economics should be followed. This was, of course, in the midst of the Cold War. Today, some 50 years later, there are dramatically different motivations for the moon. And in large measure, these are driven by the resources that have been discovered over the past couple of decades at the lunar south polar regions and the lunar north polar region, having to do with lunar ices. Just as an indication of the reflection of this global interest and consensus, this is the current membership of the International Space Exploration Coordination Group, which is responsible for coordinating between activities, putting together an overall roadmap for space exploration in general and the lunar exploration in particular. And you can see, and I should mention that in the last year, the number of countries participating in this coordination group has doubled. That's currently chaired by the someone at the Canadian Space Agency. And in the global exploration roadmap that this international group has framed, the idea of space resources, lunar ices loom large. In particular, in their global exploration roadmap, published a year ago next month, there are two key requirements, two key goals that are identified. One is a target to produce 50 tons of propellant per year from the lunar materials. This is an ambitious goal. And the other is to generate some 300 kilowatts of power on the lunar surface for a variety of lunar activities, including resources processing. And I wanted to probe today in my remarks these two numbers: how much propellant and how much power. And so I'm going to come at this from the standpoint of a design trade space and some activities that are currently being conducted by the Moon Village Association. So from the standpoint of the trade space, there are a set of requirements and constraints. For example, recent discussions having to do with the science of the permanently shadowed regions, which is where the lunar ices are, the question of whether or not and how much environmental contamination might be acceptable, and of course, for any kind of private venture, the ever-present minimization of cost. Of course, what's the principal driver here is the production of H2O from lunar PSR regolith. One key trade space question is, where do you do it? And there are a number of recent developments. I think perhaps George Sauer in a few moments will talk to one of these that have to do with processing from the regolith in the PSR. The case that I'm going to look at today in just a little detail, but from the standpoint of the requirements, is really the idea of having a remote facility, a refinery, where the processing takes place rather than in situ in the PSR. And of course, there are several different means that have been looked at, including a couple of different types of thermal extraction, either using reflected sunlight or using powered heating. And then, of course, there's the idea of doing it at a remote location. In the past, a number of different fun concepts. The idea of the 1980s of a big open pit mine on the moon, as executed by Pat Rawlings. Another Pat Rawlings image, which is the idea of building power stations around the rim of a permanently shadowed crater and transmitting power down into the darkness. And also the idea articulated in this image in the lower right by Bob McCall of a roving lunar concentrator. Of these images, these concepts, I think only the idea of transmitting power down into a PSR from power stations around the sunlit rim is still very much in discussion. This is a concept from a recent NIAC study, and it's one that I won't second guess, but I'll speculate that George Sauer might speak to this. It's the idea of in situ processing of the lunar regolith using reflected sunlight and a dome to encapsulate the regolith. And then, of course, there are a variety of concepts having to do with centralized mining equipment and mining machinery. You can see in the cartoon in the upper left two radically different kinds of mobility system. One, a more or less conventional track layer tractor. I think that's impossible, but nevertheless, it's a nice picture. And the idea of a multi-legged athlete, the JPL athlete type roving vehicle doing in situ fabrication using regolith. So with regard to terrestrial mining, this is the direction that terrestrial mining is going. It's going all electric. And these are some images that I grabbed from online sites in the last couple of days, which reflect this new direction for mining. As the world drives towards carbon zero systems, mining is one of the areas where enormous amounts of diesel fuel, a lot of CO2 and methane are released. And so the mining industry is trying to go all electric. And that includes electric machinery, such as in the lower left. It also includes electrical transportation, such as trolley lines, but also electrical equipment down underneath the earth. And one of the forerunners in this, who you'll also be hearing from later this morning, Jim Caravella, is Off-World. And in this case, an all electrical fleet of modular, smaller robotic systems is being developed to do terrestrial mining, and also in the longer term to do mining on the moon. And I think as a vision, this is a real leading concept to transition from the all electrical terrestrial mining to all electrical off-world mining, pun intended. So now to the question of the study that we're doing within the Moon Village Association and these two key numbers: how much propellant and how much power. So this is a high-level context for the lunar village of the Oasis 2045 case study that the Moon Village Association is doing. It shows the region to the between Shackleton, the Gerlach, and Sverdrup, the lunar South Polar Ridge, which is one of the relatively sunlit locations at the South Pole. This is a location that NASA's looking at as one of the places where the first or the next human landing might occur. And the concept is to place a settlement at sort of in between three of the four major ice-bearing locations. One, this diamond-shaped area above, two, de Gerlach, and three, Sverdrup. These are just some terrain maps of the locations in question. And in looking at these, it appears that there are pathways such that surface mobility, surface access to each of these three sites is achievable. I don't include Shackleton because the Shackleton crater is extremely steep. The difference in elevation from the rim of the crater to the floor of the Shackleton crater is on the order of 5 kilometers over a distance of about 6 kilometers. I don't think there's any reasonable expectation that in the near future that surface access to the floor of the crater is going to be tractable. But from these other locations, for example, I show here a notional route. It should be possible to go from the central processing refinery envisioned at Oasis to the three ice mining locations that are indicated. This is just a zoom in on the habitation site and this end of the lunar South Polar Ridge. In particular, this crater is the location for the Oasis 2045 habitation that we're looking at. Across the ridge and safely about 4 kilometers away is a location that we're looking at for a spaceport. And in between these two, there is an impact feature, which is very interesting, which is essentially never gets above about 100 degrees Kelvin. It's not a site for ice because it does get a little bit of sun, but I think with just a little bit of engineering, that this hole could be turned into a cryogenic pit. And the idea is to offset the requirement for energy to liquefy LOX and hydrogen by making and storing cryogenic propellants in a pit. And therefore, you don't have to provide the energy otherwise. You just need to provide the radiative cooling. This is a same locations, but showing a beautiful false image made from the Lunar Orbiter Laser Altimeter data of the Lunar Reconnaissance Orbiter. And this is available at JPL if you want to go and look at it. You basically see the whole moon with LOLA data. And this is just a zoom in of this particular location. You can see the pit here that we're considering for a cryogenic propellant depot. And the beauty of this is, of course, it's at the far end of the lunar South Polar Ridge, is that there is a trail all at about 1,575 meters elevation from the settlement to the pit, to the propellant depot, to the spaceport. And so you can envision cutting a road along the ridge line and have a flat road with no bumps or rises or falls from A to B to C.
How many more, John?
Oh, I'm coming right up on it.
Okay.
So here's the concept of operations as I described: a central facility for the spaceport. This is a model that's been developed for putting together an integrated analysis of these various elements. The two case studies that I mentioned, a lunar travel and tourism propellant use case model and lunar agriculture use case model, basically walking through what are the various stages of going from regolith to refueling a vehicle and regolith to having water for agriculture. This is the reusable lunar lander case, and I just wanted to highlight that that it works out to be approximately 180 metric tons of regolith per reusable lander launch, with a presumption of about 9 metric tons of LOX hydrogen to carry a payload of about 8 metric tons. And that works out to about 450,000 kilowatt hours for each launch. And if there were 2 launches per month, that's a requirement for about 1.5 megawatts. So the 50 metric tons that was identified is a good number. The 300 kilowatts is probably on the low side. However, for the lunar agriculture case study, I won't go through all the details of how many square meters per person, but just suffice to say that for a modest-sized lunar settlement, for each person, you need about 1,250 square meters of agricultural land, and that requires approximately, assuming that the regolith is 5% by mass of water ice, requires about 10,000 metric tons total for the agriculture. For 40 settlers, works out to be about 25 million kilowatt hours. But if you do it over 10 years, only works out to be a power of about 300 kilowatts. And so the power needed for the agriculture is much more significant. Closing, for an integrated lunar spaceport and settlement, the architecture suggests that a common family of rechargeable electric vehicles can do the mining, the regolith hauling, and so on. The transportation, i.e. taking the ice-bearing regolith from the ice mine to a central refinery rather than processing it in situ, only represents a tiny fraction of the total energy required for either of these use case models, on the order of 14%. And so given the other elements and convenience and so on, it seems like a worthwhile option. And it would facilitate a set of strict protocols to capture science data while you're doing the mining and to minimize any release of volatiles, because the actual processing at the refinery would be done within a closed environment. Additional studies are underway and will be presented at the upcoming IAC 2021 in Dubai.
Thank you, John. That's great. Good introduction, good history for a lot of people unaware of it, unfamiliar with it.